So one of the main topics in the early part of real analysis for us, section 1.3 and 1.4, is some axiom that guarantees that the real numbers, so to speak, don't have any holes or gaps in them. So one way that you can arrange for that is by invoking the axiom of completeness. And so that axiom says every non-empty subset of the real numbers that has an upper bound must also have a least upper bound, or a supremum. Right, so every bounded non-empty subset of the real numbers has a supremum. Now it turns out that the axiom of completeness implies what we call the nested interval principle, which is a different way of specifying that the real numbers don't have any holes or gaps in them. And I think in a lot of ways the nested interval principle is actually a little bit more intuitive than the axiom of completeness. So I thought we would take the time to show that if you assume the axiom of completeness, then that implies the nested interval principle. Right? So the nested interval principle says that if you have a bunch of closed intervals in the real numbers, and they're nested, which means the nth interval contains the next one. And so this relationship specifies that if you start with a first interval, then the second interval is contained in or perhaps equal to the first. The third interval is contained in perhaps equal to the second. And so you have this infinite sequence of nested intervals where each interval is contained in the one before it. As you'll see in the homework, the hypothesis that you have closed intervals is important. This doesn't actually hold true if you allow open intervals. So the nested interval principle says that if you have a nested sequence like this, and you take the intersection of all the intervals together, then there has to be something in it. Right? In other words, a nested sequence of closed intervals in R has non-empty intersection in R. And what that means is, if we want to show that this is true, we have to produce an element that is in all of the intervals. That's where the axiom of completeness comes in. All right, so we're going to invoke the axiom of completeness in kind of a clever way to get the exact thing that we need. But first, let me sketch out on the number line kind of the picture of what the nested interval principle is telling us. So we start with some closed interval, say A1 to B1, and then inside that interval we have another closed interval. And then inside that interval, yet again, we have another closed interval. And that process continues indefinitely. And so the news of the nested interval principle is that somewhere there's got to be an element that's in all of the intervals. Right? In other words, it's in the intersection. So the way we get at this is we're going to take all of the left-hand endpoints together as a set capital A. So let A be the set of all the left-hand endpoints for our nested sequence of intervals. Well, because of the way the intervals are constructed, A is bounded. It's a bounded set of real numbers because it's bounded, in fact, by every single one of the right-hand endpoints. Right? The left-hand endpoints never pass the right. So A is bounded above by every one of the right-hand endpoints b sub n. So now we have a bounded set of real numbers, and the axiom of completeness guarantees a supremum for that set. So by the axiom of completeness, there exists x equal to the supremum of the set A. And it turns out that x has to be in the intersection of all the intervals. So that's the last bit to prove. If you take x to be the supremum of all the left-hand endpoints, that supremum falls in every single one of the intervals and therefore in the intersection. So we claim x is in I sub n for all n, and hence in the intersection of all the INs. All right, so why is this true? First off, we know that x is larger than all of the left-hand endpoints because x is an upper bound for A. All right, that's one piece of being the supremum. It's got to be an upper bound. The second piece is that it's the smallest of all possible upper bounds. And that's where the BNs come in. All right, since x is the supremum, and since each BN is an upper bound, we must have each of those upper bounds is bigger than or equal to what we have already shown or guaranteed to be the smallest possible upper bound. But these two things, these two facts guarantee us what we need. If x is always bigger than every left endpoint and smaller than every right endpoint, it's always in the interval. And if it's in all the intervals, it's in the intersection. So that completes the proof. If you assume the axiom of completeness, that every non-empty bounded subset of the reals has a least upper bound, then you also get the nested interval principle, which for me at least is more intuitive as a way of kind of saying there are no holes or gaps in the reals, right? If you have this sequence of intervals that's a nested sequence, they're closed intervals, and you intersect all of them, there has to be something there in the reals. All right, so that'll do it for this video, and I will see you in class.